So let's look at this particular example. Let's construct a robot. This is exactly the same, hold on, this example. All right, let's just use this example and to see how we can use this product exponential compute or to verify the formula, at the same time to see how we can use Drake to build a robot from scratch. Okay, this is simple enough so that we can develop or build this robot from scratch. All right. Okay, first of all, you need to set up Drake. I assume you know enough background about Drake. If you don't, spend some time. I think homework 3, we will give some problem related to Drake, and you can use it to to solve many different problems. In this case, let's see how we can. Let's run this first. Let's load all the packages. I start some kind of Mascat visualizer as localhost. Then what I'm doing here is just building that robot, okay? And this robot, as I mentioned before, is just nothing but several bodies interconnected with each other through joints, okay? In this case, how many bodies we have? Let me just explain a little bit. In this case, we have 3 bodies, all right? Let's call that 3 of them. That's we have 3 bodies. Okay, the first body, if we want to draw somehow closer to this particular look we gave in this example, and the first 0 body or link 0 is a cylinder. Okay, let's call that link 0. Okay, and we also have 2 kind of other links, link 1 and the link 2. Okay, so we will draw it. There's 3 of them. Let's call that. This is a box. Okay. That's one link. This is the link 1 and link 2. Okay. That's our link 2. Before you assemble them, before you interconnect them, they have their canonical look. They may look like this, right? Your job is to put them together at appropriate locations. Okay. Its body, and whenever you define a body in any kind of URDF or even in Drake, you have to be aware that there's some kind of body frame locally attached to the body, right? In this case, let's take our view. This is maybe X0 head. This is Z0 head. This is Y0 head, right? That's exactly what we have here, right? And this link 1, I also attach a body frame to the bottom because for some reason I want this one to be so the Z direction I want it to be along with the height of this box. Okay, so this is a Z1 head. This is X1 head. This is Y1 head. Okay, I hope you know what I mean. Here is, I attach another one. This is X2 head. This is Z2 head. This is Y2 head. Okay, I define a body. I define a local body frame. Now my goal is to connect them. Okay, so I need to connect them in a way that I can construct a robot like this, right? So, so in order to connect them, I need to define where the connection, where the joint is, right? So I need to define joint frames. For example, the first joint, okay, the joint 1, let's say joint 1. The joint 1, if you look at this figure, is here, right? And so in joint 1, I can define a frame on body 0 that denotes where I want body 1 to connect with body 0, right? And this joint, if I want to make sure everything aligns well. So so I would say this is my Z direction, this is my X, this is my Y. Okay, Z of joint 1, Y of joint 1, X of joint 1. I hope you can see clearly. Then I may ask Hongbo, all right, if I somehow connect, let's say I connect this frame 1 to this joint 1 frame, I assume it will be exactly this part. We finish this part construction. Do you agree, or do you have any questions?
I think this is okay.
Okay. So in space, I only have 3 kind of bodies, right? And they each have a local frame. Now I need to tell the system how their frames are related. Okay, so I'm going to tell them, all right, this joint frame I defined on body 0 is exactly co-located with this body frame of link 1. Then this box will somehow, if I connect this, then this box will be connected like this. Okay. My drawing is bad, but I hope you can understand what I mean, right? Okay. Then I need to define joint 2. This is joint 1. I want to say what's the joint 1, let's say T joint 1 frame, let's say T of joint 1. This is R joint 1 and the P joint 1. Okay. Homework, can you tell me what R and the P is with respect to the body frame of 0? Okay.
Well, the rotation should be the first column is 0, 0, -1.
So okay, anyway, so that's only rotate. Let's call that rotate. Okay, rotate about this y0 axis by half. Rotate about let's see. Rotate about this y axis by half pi, right? So that's my orientation of the new frame, right? And this P is along this Z coordinate. This is IO0, right? So that will be my 0, 0, IO0, right? But that's okay?
Sorry, I'm still kind of confused with.
Okay. This is my YJ ahead. What I mean is that this joint 1 frame is obtained by rotating the link 0 frame about this y0 axis by half pi, right? You do this by half pi, then the Z direction will point to the right, right? And the X direction will go point downward now. Okay, I hope that's okay. And also this P is moving up to this center of displaced along the Z direction by L0. So let's not call that configuration. Let's just say the notation in Drake that's related by these two is rotate and the displacement that you can place this frame relative to the link 0 body frame. All right. And now I can point joint 2. If I want to say joint 2, this joint actually the same as suppose, except the links are different. They are exactly the same, right? So joint 2, I can draw it again here, will be exactly the same. Okay, that's my X joint 2 head. This is my Y joint 2 head. This is my Z joint 2 of head. okay? And if you move this guy, this color is bad. If you move this guy to here, and you know this guy already been put in here, then you connect them, you have the 2R robot, okay? In this case, the join to relative position is nothing, right? It's identity and also displacement along Z axis by L1. Okay, I hope that's clear. So all we want is that these are something you write down on the paper, then you can, there's functions to allow you to do this. So that's what I'm doing here. I arbitrary, let's say this is, you can see my screen, right, Hongbo?
I can see that.
So let's define, these are parameters. Okay. I define the length of each body. So the parameters, these are length of body or length zero. Similarly, and this is the color, and let's call it color 1. Let's make it different color 2, color 3. That's each body has a color. I want to assign different colors. Maybe I would say this is 0, this is 0. Okay, I have 3 colors. Then I first create a multi-body plant. Okay, this is almost an empty thing. Okay, so far I don't have anything yet. Okay, then I create a instance of the model. I start to add bodies. Okay, these 3 lines of code add its body. So after these 3 lines of code, what we have is just these 3 things, but we don't know in the system with some local coordinate, but we don't know how they are related yet. Okay, and we don't know how their geometry looks yet. So that's only add 3 bodies, and we call them link 0, link 1, link 2. And these links is added to that model instance we just created, which is called my robot. Okay, and when you create or add a body, you have to give them some inertia properties, and this doesn't matter for kinematics example. So I randomly pick one that don't report error, then that's fine. I don't think this is correct yet. Okay, so this part is only for the sake of make sure I can add a body. So after these 3 lines of code, I have 3 bodies here. Okay, now this is similar to URDF as well. So now we need to tell the system how each body looks. Okay, and the first one, the body 0, looks like a cylinder, and so I can plant registry geometry, and this cylinder is a standard geometric shape supported by Drake. So I just need to specify some parameters, and I tell them link 0 has a cylinder shape. Okay, and this cylinder shape, also this is a color. It has a color. Let's call it color. Color 0. I should change that to 0, 1, and 2. Okay. So this is the color 0, and this name is called link 0 and has a shape. And this cylinder has a relative orientation and position relative to the body frame like this. Okay, so typically the geometry has its own kind of, let me see. It's typically has its own body frame, the shape frame, okay, the geometry frame, and I have a body frame I choose by default here. So when I place this cylinder, I should place it along the Z direction by half of this L0. Okay, that's how I do it. If I don't, so that's where I have the Z direction have L0 divided by 2. If I don't have this, then almost like the body frame is in the center of the cylinder. So this is not what we defined before. You look at this figure, this is our frame we selected. It is not in the center, so I have to place the geometry a little bit above this ground, okay? That's what this line of code means. And then, hold on. So now let's, I think that's only one. Where's the others? Let me, we need to write down the other two. The other two is not cylinder anymore. This is a box. I think it's a box. Let me see. This should be this is the box. Box has a 3 dimension. Let's call that C. C is the somehow the this part, okay? And let's call that height, width. Oh, sorry, length, width, height. Anyway, so this small dimension is C. I define the C as 0.5, and this is the height is L1. This is called L1. Link 1, okay? And I also place, I think that will be half of L1. This is, I think that's wrong, that's box, like this. This is the code, link 1, this is that, okay? That's Regis geometry, that means body 1 or link 1 has a box. It's cube, right? And 3 dimensions is C, C, and L1, and I place them up halfway through the height. Okay, so this is, let me copy that again. That's, sorry, link 2. Let's change that to L2. That's L2. This is the link 2. Okay. Now, so far, we have a local body frame and also the shape correctly defined, hopefully. And then I need to specify joints. How do I connect different bodies? So I need to first define my joint frame 1. And this is joint frame 1. And I have to add a frame, attach a frame to the first body, link 1, link 0, all right? And this one has a rotation about the y direction by half pi and 0, 0, L 0. So that's where this frame means. You have to use a fixed frame. So that this add frame means you add to that body, this link 0, a frame. It's a constant frame. And this frame has a homogeneous transformation matrix specified by R and P. This is rotate about y direction by half pi. And this is the displacement about z direction by 0. That's exactly what I write down here, right? And then I can do a join 2. Join 2 is attached to the body 1. And let's see. And this is attached to the body 1. And the orientation is the same. Also displacement along the z direction by L1. Okay, that's this one. So after I specify the frame, now I can connect bodies. Connect body means I introduce add a joint. That's plant.add joint, and these joint have different types. In this case, it's called revolute joint, just our rotation type of joint. And this is my joint name. And so adding a joint mathematically, just you want to make sure some frame on the parent body, which is the link 0 here, and another frame on the children or link 1 body, they are, you recognize these 2 frames are the same, okay? In this case, my parent frame is joint 1 frame here, and my children frame is, I directly use the body frame of link 1. I make them the same. So then I almost like moving that box here and attach to that, okay? Then I need to specify the rotation axis. And rotation axis, Fuzhen, I'll ask you, what's the rotation axis here according to, because these two frames become the same, right? You align these two bodies by connect these two frames. What do you think the rotation axis is in this case? According to this frame, okay, the joint frame, what's the rotation axis?
Rotation axis.
The joint along which direction? XJ1, okay? Is X or negative X?
A negative X.
Negative X, right? Because we call this rotate about this direction, it should be upward, okay? So negative X is the direction, so that's why I say the X is -1, that's X dimension 0, 0. Okay, and joint 2 is I recognize, I tell the system, this frame on body 2 is exactly this frame on body 1. Okay, I connect these two, that become a joint. Okay, and then the rotation axis is what? Fuzhen, can you tell me?
The rotation axis.
Look at this, right?
XJ2. Negative XJ2.
It's negative XJ2, yes. So it's still negative X, right? So this according to the joint. Those are other parameters, and what's the range of this joint. So overall, I have two joints. I also need to tell the system this guy is the 0 frame is S frame. Is a fixed frame. Let's say 0, S are the same. I tell the system 0 frame is just S frame. I just say plant weld frames, and these two frames are weld together. It's not a joint anymore. It doesn't move. It doesn't have axis. It's fixed together. All right. So the link body frame become the word frame. Okay, and there's no kind of rotation or change. Okay, so far I just put all of them together. Now I have this whole thing. All right, I haven't specified what frame I'm interested in. So suppose this is my body frame. This is B frame. I will define it as G here. Okay, this G frame, the body frame is attached to this B frame is attached to the link 2, body 2. So I also add a frame. This is called anti-factor frame or B frame in this case, and it's attached to link 2, so it will move with link 2, right? And the transformation about the link 2, if you think about these are the dimension, these are the body frame. See that this is the body frame of link 2. What do you think about this B frame? So it's actually, I think it's rotate about Y by half pi, right? By negative half pi. Is that true? Rotate this frame about Y by half pi will come here, and then it's negative half pi, it's to here. So that will be the B frame. So that's rotate about Y negative half pi, and also displacement along Z direction by L2. So that's my B frame. Hongbo, is that clear now? The syntax?
Yes, clear.
Okay, right. So you can construct, I'm going to ask you to do that in your homeworks, okay? Simple robots doing this, okay? It's almost like you write down your own URDF file. Right? It's not easy, but it's a good exercise for you. At least you need to do this at least once, okay? So we can run this. Okay, seems everything is okay. So this is a special form, a special function in Drake that they draw the coordinate system, the X, Y, Z. So if you give them frame names, so I add them so that they will displace they will display them in the simulator. Okay. So after that, plant finalized means you finish specifying the plant, and there's some kind of other works you need to do, and then you start the simulator. Okay, so far, let's see. That's maybe our hold on. Okay, that's our robot. Why these two are the same color? Let's see. Let me do this. Oh, okay, I see. I forgot this is changed to color 2, right? Let's run that again. Run that again. Run that again. Okay, that's become 2 of that. So currently, that's my robot, 2R robot. Okay, and this is my B frame. Okay, this is my 0 frame. So that's our 0 position, but we can set the position. Let's say this is maybe pi, numpy dot pi divided by half. This may be numpy dot pi divided by 3. If I set these 2 theta to be this position, I can set positions. Let's compute, let's run it. I think it will move. All right. So the second joint rotate by half pi, and the first joint actually rotates 1/3 of pi. Okay, so that's looks. And now we can compute, right? This anti-factor frame has a pose in the word frame. Okay, we need to compute that. In Drake, they can directly say, because I attach this anti-factor frame as G, right? I define it as G, and after I set the positions, I can say G calculate pose in word to give them context. Context means all the information you need to do the simulation. Then I can find this is a TBS, okay, at current theta 1, theta 2. That will be this rigid body transformation matrix. Okay, that's my things. Okay, now let's do some hard work. Okay, let's say now let's verify using PoE. Use what we have learned so far. How many steps we need to compute this the TB in S as arbitrary theta? First of all, let's import. I think I downloaded Modern Robotics as MR, because our notations similar to Modern Robotics. I would just import their packages, so it will simplify something. Step 1 or step 0, what is it? Yangxing, what is step 0?
Sorry.
What is the step 0 to compute our, hold on. Let's look at our derivation before, right? Step 0, compute M. Okay, so when all the theta are 0, you compute the current configuration. So build M. What is M in this case? We already derived it, right? So M is something you need to figure out first. Hold on. This is M. Where's M? M is these numbers, right? So M is the homogeneous matrix. His part is identity. This part is L1 plus L2, this guy. Okay, so I think that's my M equal to MR dot. This is, I think, RP, the rotation matrix and the displacement vector to homogeneous transformation matrix. You need to tell them R first. R is numpy dot identity 3 by 3 matrix. And this numpy dot array, this is L1 plus L2, that's first element. Second one is 0. Third one is L0. Okay. We can print M is this matrix. Okay, 4 by 4 matrix. That's our M first step. So step 1. What is step 1? Here, let's compute all the screw axes. Okay, screw axes. So, what is let's say what is ice? Let's say in this case we have 2 screw axes. First one is IS20 bar, right? IS20 bar, and that's how we compute it. That's actually, we can directly type in, but we can also use the function, the modern robotic function to find it. Let's call the IS, bar 2 in 0. That's my notation for now. Okay, that's IS bar 2 in 0. It's modern robotics screw 2 axis. Screw 2 axis. And basically, you tell them Q, you tell them S direction, this is 0, right? Keys, then they will tell you the corresponding screw axis. We computed already, but we can verify that again. So what is the Q2? Q2 is, let's take a look. Q2 is 0. No, L1 00, right? So that's numpy dot array L1 00, and that's my first. Second, it's numpy dot array. That's the direction, which is 001. That's omega, and the pitch is 0. So overall, we will have this. Let's see, what is it? S bar 20 is a 6-dimensional vector, 001 negative half, which is this one. All right, that's what we computed. That's the, I think it's the same as the package returned. Similarly, we will do this again. So that's as this is 1 in 0. This guy is, I think, Q0, Q1 is here. Q1 is here, 000. So, and the direction is the same. So we have these 2 screw axes, right? Now we have these 2 screw axes. All we need is type in that matrix exponential formula, right? Let's define our own kind of function. Okay, that's my PoE. That's my function. Theta 1, theta 2. We need a function, right? We need the analytical form. Sorry, this is theta 1. Okay. And so S bar, the matrix represents of the screw axis. That's a matrix 2 and 0. What I'm trying to do now is this guy. Okay, the matrix representation of this times theta 2, and that's I think MR has the convenient way to do it. This is vector to SE3. Okay, the matrix representation of twist is in SE3. That's our what? S bar to 0. Okay. Similarly, we will say this is 1 in 0, 1 in 0. Okay. Then I can, if I know this matrix, I can say return MR dot matrix exponential exp6. This is let's see. So this is S bar matrix. This is this one first. Times theta 1. Matrix multiplied by MR dot matrix exponential 6. This guy times theta. Oh, sorry, this guy times theta 2. What I do is sorry. I think you need to also multiply by m. Okay. So what is computing this is nothing but this exponential form, right? So this is a matrix exponential 6, this multiple 6 given vector, then times m. I think that returns the overall TB in S. Okay, so we can test. I think our theta 1, theta 2 already specified before. Let's just say print. No, let's say TBS equal to my PoE theta 1 and theta 2. And let me print TBS. Hold on, let's see. Is this correct? So this is the displacement vector, negative 0.6, negative 0.6, 0.93, 0.8. And this rotation matrix is negative 0.6. I think this should be correct, right? So that's exactly the same. If you specify different, let's try different things, you will have a different configuration, joint variables, and this guy has a different pose in the word frame. And based on our own function, we should be 0.5, 0.8, 1.8. Roughly, I think it should be correct. Any questions? Was there any questions? You think it's okay?
Yes, it's okay for me.
Okay. So the forward kinematics is nothing but this. If you gave me a robot, you just first find out the screw axis, and in the 0 configuration, you find out the home position pose. Then matrix of exponential formula is just like that, right? Very elegant, just a few lines of code. And we cross-check it with the built-in function in Drake. Okay, and in the homework, I think you need to verify. You need to do a few more examples. Of course, it's more difficult than what I gave in class.